Last week we have basically introduced one approach, which is something called the numeric iteration. This one we have three methods we introduced. We introduced the forward, backward, and historical. Okay. And this week we are going to continue for the other two. One is the comparison and another one is the sample and fold method. Frankly, these two methods is not something totally new to all of you. We have actually learned both of them before. Around week 3 and week 4, we have when we introduced the Z transform. When we have introduced the Z transform, we have done certain comparison between the S and the Z, right? We have done certain mapping from S from M to Z. And at that time, we talk about the S and Z in view of the Z transform. So through certain similarity between the Laplace transform and Z transform, we hope you can very easily predict whatever you have learned in your continuous domain to your integral domain. So if you assume you have learned pretty well in your dynamics control, you have a very good understanding about social stability, social about response, and so forth in S domain. After we introduce the Z domain, after we introduce the stability control, you can have a very simple comparison. Okay? So that is the method. And today we are going to introduce some of the specific techniques. Okay, how to really convert S function to a Z function so that we can find some so-called discrete equivalent, okay, digital functions from a continuous control function. So today you can consider this one as a specific application or a certain particular technique, okay, to implement the mapping from S to Z. And frankly, this module in my part, the major part is about conversion, right? It's conversion from your analog to digital, conversion from S to Z, conversion from your continuous to discrete. So one of the basic or very important idea is the mapping from the S domain to Z domain. Okay? And after the day we will have a full picture, okay, about that. And then the second part about the sample and fold. This is something actually we also have learned of week 7 and week 8, right? Sorry, week 6 and 7. So week 6 and 7 we have talked about the signal, right? Through the sample, through the digitization, being able to convert the analog signal into digital signal. Then after we have done the digital control, we have digital control algorithm based on the digital input, based on the digital control algorithm, the digital control function. So you are going to have the digital output. But the actual physical plan, the actual mobile, the actual voltage generator, the actual pressure valve, and so on and so forth, all continuous plans. Right? So you may need to have a certain conversion on your digital output to your analog output. So that is something we call the sample and fold. And today we are going to further elaborate the sampling and fold and to see now from an overview picture, from a systematic point of view, are we able to have some mathematic equivalence from a S function, from a continuous control function into a digital control function. So today we are going to further introduce these two methods. But before we move on to the two new methods, let's have a quick review for what we have done last week. So last week we have basically talked about the numeric approach. And for the numeric approach, basically is the numeric approximation for differentiation or integration. We have the forward, we have the backward, we have the trapezoidal, right? So based on this, and we really hope you can have your full attention. We have 11 weeks. If you lose a little bit attention for 9 weeks, 1 to 7, and also next week is 1. Last week and this week, okay, must be good. Okay, the reason I told you already, I still the reason I cannot tell you again. So for the forward method, backward method, trapezoidal method actually pretty simple. After certain derivation last week, we have come up certain approximation of your S operator, depending on different method you are adopting, right? This is your, if you are using the forward rule, then you just use z minus 1 divided by t to replace your S. What is t? The later in the exam, you don't tell you what is t. They won't give you a t, right? So what is t? If after today you don't know what is t. You week by day, you know that what is t. It's your sampling time, right? Is that right? Okay, so you use z minus 1 divided by your sampling time to get your S function. Okay, very simple. You have a transfer function. For example, this one, a divided by s plus a. Then you just replace your s by all those approximations for this boundary. Is it simple? It's simple, right? So these are the three methods: forward, backward, and backward. And after that, okay, please bear in mind. Your stability criteria in your S domain may not guarantee your stability in your digit domain after you have done this approximation, right? Last week we have done certain comparison, the domain mapping for your forward method. You are not necessary for your stable to be a stable domain, right? Because that one will map to all the left-hand side of your positive one, right? So if sometimes in your S function is a stable function because your poles are all negative, or all on the negative domain, all on the negative side. But that's not necessary to see your negative and convert to your unit circle, right? You need to make this something that you have in mind. But anyway, for the derivation for this type of equivalence approximation is really simple. You need to remember this trait, then depending on which method you are asking, you just substitute in. After substituting, you are able to find out where is the pole, whether how is the stability and so forth. Okay, similar things and what you have enjoyed. Okay. And today we are going to introduce another two methods. And the first method is about pole and zero equivalence. So for this one, first of all, you need to relearn what you have done in your lattice control. Give you a transfer function, are you able to find out the poles and zeros? Are you able to? Yes, right. If I give you a transfer function, you don't tell me after today you cannot find the pole and zero, then I really cannot help you for this one. Okay? So first of all, you find the pole and zeros, okay, in your transfer function. Then after you get your pole and zeros, then all the poles and zeros will be mapped according to a function which is z equal to e power st. This is something we have introduced when we introduce the Z transform, when we introduce the mapping from the S domain to the Z domain, right? So what I mean is, if you have a transfer function HS, so for your HS, if let me see, you have something for this function, are you able to find out what is the pole, what is zero? Yes, right? Don't shake your hand, don't shake your hand. So this one, But for the zero and pole matching, there is one thing I want you to be aware. Because for the full and zero matching, if there is no delay, then how many number of zeros you should have how many number of poles? So what we mean is actually there's some hidden zero, they may have some hidden zero or poles in your function. So for this case, what do we mean for zero? What's the meaning for zero? What's the meaning for zero? Zero now appears like a solution when this one equals zero. But the actual definition for the zero is if your s is equal to the zero value, you substitute the s into your transfer function, your transfer function will get s. Will get zero, right? Alright. So for this case, how many zeros you actually have? Is it only one? Is it only one zero? Under what scenario you will also get your transfer function to be s, besides when your s equals to this? Do you have any other scenario? I can also look at the top, you know, like this control. Maybe I can teach you like this control. Okay, so for this one, when your s goes to infinite, how much will be your value? This one you have done your math, right? If your s limit to infinite, approach infinite, how much will be the transfer function? What? Huh? Very small. Very small. How small it is? Infinite small. Infinite small is what? Infinite small is zero, right? Because this one you only have first order s. This one you have a second order. Right? So if I put the limit when my s equals to infinite, then this one will go to infinite because you can simply, if you want me to show you as many as I do, I also can teach math. Alright? If you do the limit when s equals to infinite, this one is 1, this one is 0, this one is infinite, this one is 4, this one is 0, what do you get? 1 over infinite, what do you get? 0. So you actually have another hidden 0 which is infinite. Usually for transfer function, you are talking about 0 and poles, the number of 0 and poles should be the same. If they are not the same, it means, for example, in this case, you have 2 poles, 1 0. It means actually you have another 0, but just the 0 is infinite. It's not a finite number. It's not a infinite number. Okay? And this is something maybe very, very important you may need to pay attention. Otherwise, this message is confusing. Because everybody knows how to substitute s with z power. Z equals to e power minus e power of st, right? That's why it's simple. But usually the student may be a little bit confused, don't understand. Why sometimes you have another 0, why sometimes you have? Okay, the principle is very simple. The number of poles and the number of zeros should supposed to be the same from the mathematical point of view, right? The number of poles means what's the value of your s when your function will go to infinite. So in this case, if your s equals to minus 3, your hs will become something divided by 0, right? It's infinite. This is when your s equals to minus 1, this one becomes 0. This one is some defined value, minus 1, minus 1 plus 1 is 1, right? So when your s equals to minus 1, your hs function will become infinite. So actually in mathematics, the meaning of the code is the value of s and your function value to be infinite. And the 0 means the value of your s after you substitute in your function to be 0. And mathematically, the number of poles and number of zeros are supposed to be the same. Okay, but we understand in your dynamics control, you can learn your order 1, order 2, and so on and so forth, right? Also, function it just means your number of poles is 1 or 2, then the number of zeros, right? Now, where is the 1 and 2? They are hidden. They are hidden somewhere, untouchable, unapproachable, but they consider as infinite. This is something important for this type of method because we are looking for the equivalent. So we must find all the possible hidden zeros. Okay? So for this case, you have 2 zeros, you have 2 poles. And then the next step is we are going to do the matching. How to do the matching? Very simple. So if you have S, you just replace your S by the Z, and the Z will be e power ST. So in this case, okay, I'm not asking you to replace this S. This S will be replaced by Z. So this one eventually will be Z. This one will be Z plus something. This one will be Z plus something. This one will be Z plus something. But what is going to plus? Is to plus your negative 0, negative 2, right? Alright. So initially in your S function, your 0 is minus 2. Then this one will be equal to minus e power minus 2. Alright? Minus, because if you pay attention, I purposely write this one into S minus minus 2. Because minus 2 is your 0. So here your Z minus your minus 3. So e power minus 3e and e minus 1e. Then how about your infinite? How about infinite? If it's infinite, then this one will map to minus 1. Okay? If this one is infinite, this one will map as Z equal to minus 1. So you can have another one, Z minus minus 1, then become 1. So is this simple? Not finished yet. So after you have done this, basically you just have done some simple mathematics here. You find out the zeros, you find out the poles. After you find out 0 and poles, then you change, replace your 0 and poles by e power st. And your s is your 0 and s. Okay? And if you got your 0 and infinite, you replace by another 0 which is minus 1. But after that, we still need to do another thing. Because after you have done this, the gain of this one will not be the same as the gain of this one. So the last thing you need to do is you need to do the mapping again.
因为刚才讲到现在这个 S 过去 infinity 的话，你要 convert 那个 Z in Z。
So after you have done that, then the last one is you need to do the mapping of the game. Because for a digital equation, at least you make sure the total gain is the same. When your S at a certain value, your gain should be the same. Okay, as your Z value. And we are going to map with the initial condition where your S equal to 0. So we need to look at your critical. And if that is your critical frequency is S equal to 0, then you are going to typically map. When your S equal to 0, your so-called equivalent Z transform function should also get the same gain value, right? So the last step is you need to do the gain mapping. So after we have obtained this, so basically your HS function is going to map with your SZ function. But you need to make sure the gain of this one, when your S equal to 0, when your S equal to 0, your Z e power of 0d is 1, right? should be the same as when your z is equal to 1. So after we have done that, we have done certain mapping. And bear in mind, later we are going to summarize the 3 different methods. And for different methods, we have different focus. For this focus, the basic idea is we do the zero and pole analysis. So in your continuous domain analysis control, you have basically determined the pole and zeros, right? And based on the pole and zeros, we are going to estimate some of the frequency response, some of the transient response, something about the stability, and so forth, right? Because the pole and zero are important method in your continuous domain control analysis. Alright. Alright. Even you may have forgot a little bit exactly what are the relationships. I believe everybody still has something in your mind to zero and pole and right? So for this method, basically we try to make sure those pole and zero are met equivalent. Okay, after the S and zero, S and Z and E. Because this one will maintain your zero and poles to be equivalent. And also after the matching of the gain, okay, it will match the gain. Okay, so hopefully the gain, the zero, the poles are equivalent. But please always remember, there is no such thing called your continuous domain can be exactly the same as your digital equivalent function will be the same as in your continuous domain. It does to a certain extent to show you the difference. But this one only focus to make sure the pole and zero are met equivalent, but not necessarily to guarantee all the actual performance will be the same. What do I mean is, after you have done this, you get your z function. So if you have the same input to this continuous function, you have your continuous output. This one you have your digital input to your digital transfer function here. Does not guarantee your digital output will be the same as your continuous output. Okay? So you only try the best to mark the equivalence of 0 and 4. Okay, but because the continuous and digital basically due to the sampling, discretization, quantization, and so forth, certain information will be missed and certain distortion will happen. Okay, so there always the difference. Okay, cannot be the same. Okay, so later